All right, so today we're going to look at discontinuities in our rational functions, some of which we already know, maybe all of which you already know. It kind of depends, because last year was a hot mess, and we all know that. So here, on this particular picture, I have two vertical asymptotes and a horizontal asymptote. All right, we already know about those. Those are great. What is different about this picture than you normally have with horizontal asymptotes? Or maybe I should ask that differently. What is your understanding of what an asymptote is? Anybody? Because I know you know what they are. So just like, how would you verbalize what they are? It never, your function will never cross the asymptote, right? Is that the general understanding that you have? Okay, so this is a legit function. It's a real function. But check out what happens here. This right here totally crosses that horizontal asymptote, right? So you actually can cross a horizontal asymptote because horizontal asymptotes tell us about end behavior. We don't care about middle behavior. It's telling us end behavior way out here at infinity and way out there at negative infinity. So it could cross a ton right here, and we'll look at some of those. So I'm going to show you some pictures of functions that kind of are outside the norm of what you were used to looking at. And so instead of thinking about it as a line that it never crosses, it is a line that the function approaches, okay, at the ends. And vertical asymptotes you're not going to ever cross because that affects the domain, but crossing horizontal and another one, it doesn't affect the domain, and it definitely happens, okay? So here's another. So here's one where it crosses. So our asymptote, which actually isn't sketched in, is y equals 0. So this part of the function comes down, and it approaches 0 from the top. This comes down, it crosses the asymptote, but then it approaches it from the bottom, okay? Again, totally legit, because we're talking about end behavior, not middle behavior. Then we can have a function that looks like this, that crosses the asymptote an infinite number of times, because it's going to keep bouncing, and as it bounces, it gets closer and closer and closer to 0. So it's still approaching 0, but from both sides, because it's bouncing, it's still an asymptote, and it's being intersected an infinite number of times, okay? So we also have another kind of asymptote, which is called a slant asymptote or an oblique asymptote. This is the one where I'm not 100% sure if we all even saw them last year. But I have a vertical asymptote right here. Then this slanty one is my slant asymptote, right? So that when we have functions that look like this, there's our slant asymptotes, and we will talk about those today if you've never seen them. I can also cross a slant asymptote because, again, we're talking about end behavior as far as the domain is concerned. So here, this is the best picture I could find, and I know it's hard to see up here, but so this up here, it doesn't cross the slant asymptote. Down here, we go up, we cross over, then it comes back down, and then it actually approaches it from the bottom. I wish it was a better picture, but it was the best I could do. But then this one, you can see that it comes down, it crosses, and then it comes back up, and it starts to approach it from the bottom. All right, so we can cross slant and horizontal asymptotes. We cannot cross vertical asymptotes. This one I threw in for fun, because if you're not liking the others, we're not actually going to get here, but math gets really crazy and really pretty cool looking. The blue part is the function. The red part is the asymptote. So you can actually have a parabolic asymptote. Right? Again, we're not going to get there, but just want to let you know that there's like so much more out there. Okay. All right, and the function itself doesn't even look that crazy, right? I mean, this isn't even a crazy looking thing that's going on. Those are things that we can handle. All right, so with all of that said, let's look at our notes. And I know if you're sitting in here, and maybe even if you're sitting in front of a computer screen watching the video or watching me live, this is probably really hard to read, because I was sitting at my desk this morning when I put this up here, but you should have it in front of you also. So you're just going to have to rely, you have the exact same thing in front of you. They're kind of small and hard for me to see up here at the board, so just should have done a better job with that. So we're looking at discontinuities in rational functions. So most, not all, but most rational functions have restricted domains that lead to discontinuities. The types, most of which you should already be familiar with, we can have vertical asymptotes, which we've already talked about and found, horizontal asymptotes, slant asymptotes, which can also be called oblique. You talked about oblique figures in geometry. If you have an oblique prism, then it's leaning over. It's not perpendicular to the base. And you have muscles that are obliques. Where are your obliques? Yep, right here. You know what they help you do? Lean over. That's why anything that's oblique is leaning. All right, then I have point discontinuities. Anybody remember what the other word for that was? It's a longer word, starts with an R. Removable. Okay, and so we're going to say point. You'll see point most of the time, but removable is fine too. So just know that they can both pop up. Okay, so the first thing we're going to talk about are our point discontinuities or our holes. So I know at the very least you've seen graphs that have holes in them because we've done that together. Whether or not you've graphed any or found them algebraically, I don't know, but we're about to do it. So, sorry. Point discontinuities, we are going to abbreviate as PD. Okay, so point discontinuities or holes in the graph occur when a factor containing x is common to the numerator and denominator. So they have to have something in common. So in order to figure that out, most of the time you can't just look at it and know. You're going to have to factor. So we'll factor this one. That'll leave me with x squared in the numerator over, I can factor out a 3x. That's going to leave me with x minus 2. Now, although I know you know what the numerator means, I'm going to rewrite this again, which I'm not saying you would have to if you were doing it. I just want to make a point here. Okay, so that's technically completely factored, even though we most of the time wouldn't write it that way. So what I'm looking for is a factor that contains x that is common to the numerator and denominator. Well, I have that. These two are factors, and they are common to the numerator and denominator, right? So I'm going to end up canceling them out. However, this tells me where my point discontinuity is. So whatever the factor is that you're going to cancel out, you set it equal to 0 and solve it to get your x value. So that means here that x would equal 0. Well, guess what? That's solved. So my point discontinuity has an x value of 0. We'll talk about the y value in just a second. So once I figure out where my x value is, I actually cancel those out and reduce it. My reduced function is f of x equals x over 3 times x minus 2. That's my reduced function. And then I find f for my reduced function, I find f of 0, or whatever this x value is, and that's going to give me 0, right? So my point discontinuity is 0, 0. This is my reduced function. So my graph looks like this. With a hole here. Okay. So we reduce it, and then that's what we actually base our graph on. We just know where the hole is. What questions do we have? Okay, so let's look at number 2. Number 2, I'm going to need to factor. So in the numerator, this will give me x and x. This means that my signs are opposite, so it's plus and minus. And what are my two numbers? Positive what? Two and a negative 3. The denominator is easy to factor because this is called a what? Difference of squares. Okay, everybody, what is this? Differences of squares. Okay, so everybody unmute. Unmute for just a second. Because I want to hear y'all say it. Aditya? Unmute. All right, and this is a what? Difference of squares. Thank you. Everybody say it. It's why you unmuted. You didn't unmute to stare at me. This is called a what? Difference of squares. Thank you very much. Okay, you can leave yourself unmuted to talk to me or mute or whatever. So I can factor this. I get x plus 3 times x minus 3. Right, so I have this factor here that they have in common. So I set x minus 3 equal to 0, which you don't necessarily literally have to write it down because I know you can figure that out. So that means that x equals 3. So for my point discontinuity, my x value is 3. I'll worry about the y value in a minute. Because when I cancel those out, my reduced function is x plus 2 over x plus 3. So I find f of 3, and that's going to give me 3 plus 2 over 3 plus 3. So that is 5/6. What questions do we have? All right, then you do number 3. Do you have any questions at all? Did I not give you enough time? Check yourself with me, make sure you agree. And when I graph this, what's the graph going to look like? Or what is it? It's a linear. So I'm going to graph a line that has a hole in it. Is 0, -3. That's exactly what that is. That's how you get a line with a hole in it. Well, you don't have to. Right now, his question was, do I want both of those answers? I'm boxing them both so you know which function it goes with, but if it's literally just asking you for the point discontinuity, you wouldn't have to give both. And your assignment's on Delta Math, and it's very specific. You're finding this, you're finding that, but you'll find some other things kind of as you go along too, but only give it what it's asking you for. That's a good question. All right, so let's talk about vertical asymptotes, because we've already found some of those together, just based on the prior knowledge you should have, but we need to get a little bit more specific with our definition here. So vertical asymptotes, we're going to abbreviate, is VA. Vertical asymptotes occur when a factor containing x is unique to the denominator. So that word unique there, that's that important word. That hasn't been an issue for us so far with the ones that we have come across, but we got to make sure it's unique. That means I'm not canceling it out. So basically, before I do anything, I have to look for my point discontinuity. Even if it doesn't ask me that, I have to look for that because that has to go away first before I can do everything else. So on number 1, I would factor. Well, I can't factor, right? So it is factored. Nothing's going to cancel out. So this is the factor that is unique to the denominator. So that means my vertical asymptote, because basically you would say, okay, x plus 2 equals 0, so x equals -2. Your vertical asymptote, x equals -2, right? And I'm pretty confident y'all get that, because like I said, that's come up a few times. All right, so then let's look at number 2. I can factor number 2 because the numerator is a what? Difference of squares. Diego's the only one that's excited about a difference of squares. So this is x plus 7 times x minus 7 over x minus 7. So based on what I have right now, what do I know that I have? I have a point discontinuity. Now, when you originally look at this, you might think, oh, look, I have an asymptote at x equals 7. No, you don't, because you have a point discontinuity. And again, this is one where it didn't ask me for this, but if you find it, I would write it down because you might need it later, that kind of thing. My x value will be 7. We'll worry about the rest in a minute. So my reduced is f of x equals x plus 7. Right, so then my y value for my point discontinuity is 14. My vertical asymptote, it says I have a unique factor containing x in the denominator. Well, there isn't an x in the denominator, so I have none. So at first glance, it kind of looks like you do, but you don't. Because once it cancels out, you don't get to be both. It's not going to count for a point discontinuity and for an asymptote. Okay. All right, so then let's look at number 3. I'm going to factor this. So this will give me 2 times x minus 4. What is this in the denominator? Difference of squares. Okay, we have a few more people excited. So this is x plus 4 times x minus 4. And oh, look again, I have matching ones, so I have another point discontinuity. My x value is at 4. My reduced function is 2 over x plus 4. So here's my reduced function. Am I going to have a vertical asymptote? Yes. It's at x equals what? -4. And remember, they are lines, so you always write it as an equation of a line. And then when I find my y value here, this will be 2 over 8. So that's 1/4. What questions do we have? Awesome. Then you find the vertical asymptotes for number 4. How many am I going to have? 2. And it's nice that it's already factored for me. So I have x equals a -5 and x equals 0. And there's really no work at all there. Okay. Are we all good with all that? Any questions at all? Okay. So let's talk about horizontal asymptotes. Once my board cooperates. There we go. So our horizontal asymptotes, we are going to abbreviate as HA. Okay, so there's 3 different kinds we can have. So with our horizontal asymptotes, they occur when the degree of the denominator is greater than or equal to the degree of the numerator in a rational function. Okay, so we have 3 different things that could happen with a rational function. It could be top-heavy, it could be bottom-heavy, or it could be tied in degree. And we're talking top-heavy and bottom-heavy based on the degree of the function. So the top-heavy, right? So here, if I just look at the degree of these functions, now basically, yes, I could have point discontinuities in here. I could have vertical asymptotes. None of that's going to affect what's happening with my horizontal asymptote, even if I can reduce stuff. Because if I can reduce something, then the difference in the degrees stays the same. If it was top-heavy, it's still going to be top-heavy, and so forth and so on. So this one, the numerator is a degree 2. The denominator is degree 1. So that's what it means to be top-heavy. The degree in the numerator is larger. Well, this says that horizontal asymptotes occur when the degree of the denominator is greater than or equal to. Well, it's not greater than or equal to, so guess what? For my horizontal asymptote, I have none. And that's what it says right here. If it's top-heavy in degree, greater degree in the numerator would indicate no horizontal asymptote. So when I look at number 2, I have a degree 3 over degree 2. It's top-heavy. So for the horizontal asymptote, it's none. Like, I still have to answer the question, even though there isn't any, but it's none. Okay. If it's bottom-heavy, which this is, the degree of the denominator is 1. What's the degree of the numerator in number 3? It has 1. What is it? 0, because if I had to put an x in there, the exponent on the x would be 0, because anything to the 0 power is 1. So it is bottom-heavy, right? So it says bottom-heavy in degree, greater degree in the denominator indicates horizontal asymptote at y equals 0. So if I can identify that it is bottom-heavy, then it is y equals 0. There's no work there either. This one, it's a degree 1 over degree 2, so that makes it bottom-heavy. Horizontal asymptote, y equals 0. So horizontal asymptotes are super simple. You just have to keep track of what is, which one goes with what as far as bottom, top, and tied. So if it's tied in degree, then the degrees are the same. Okay? So here I have a degree 1 over degree 1. When that happens, if it's tied in degree, it leads to a horizontal asymptote where y is the ratio. Ratio should make you think of what mathematically? Say that again? Okay, something dot dot something, which it totally could mathematically too, but what's another way to write that? I think somebody said it. A fraction, yes. So ratio mathematically, and again, you can totally write them that way. That is a ratio. But when we see it in problems like this, it should make you think fraction. So that's how I'm going to write my ratio. It's the ratio of the lead coefficients of the numerator and denominator. So I find my lead coefficients. My lead terms are 2x and 5x. So that means that my horizontal asymptote is a ratio of those two. It's going to be 2 over 5. Y equals 2/5. When I look at number 6, they're tied in degree. I get 2 over 2, so that means y equals 1. That's how you come up with your horizontal asymptotes. That's simple. Always simplify, yes. Okay. Then we have the slant asymptotes, which we will abbreviate as SA, but another word for that you might see is oblique. So I want to make sure that you know the word that goes with it. So here's how this works. So it says slant asymptotes occur when the reduced rational, it's the reduced one, which means we got to get rid of the point discontinuity first. The reduced rational function contains an x in the denominator, and the numerator is 1 greater in degree than the denominator. So if the numerator has to be greater than the denominator, it's top heavy. So the only time I could have a slant asymptote is if it's top heavy, and that's why there's not a horizontal asymptote. But not only is it top heavy, it's important that you realize it says 1 greater in degree. So this is x squared over x. That's 1 degree greater. If this was x cubed over x, no slant asymptote. Okay? Then it is found by dividing the numerator by the denominator. Okay, so it's the reduced function, which means that we have to factor this first. My denominator is going to stay x minus 2. And then this is going to give me x and x. It'll be -1 and -3. So am I going to have a point discontinuity? No. So basically the function they gave me is the reduced function. And since I want to divide the numerator by the denominator, I actually want to use the original form to be able to do that. What kind of division would you prefer to use? Synthetic or long division? I'm going with synthetic too. So a 2 goes on the outside, and then this 1, -4, and 3. Always check to make sure you don't have any missing terms there. So I'm going to bring down my 1. This is 2, -2, -4, -1. So the slant asymptote is y equals, and then this is just going to be x minus 2. Now, I have this -1, so the actual division gives me x minus 2 plus -1 over x minus 2. However, when you divide to find the slant asymptote, you just ignore the remainder. You will always have 1, because if you don't, then it divides evenly and you should have reduced something out. Like, that's a problem. But we just ignore it. So it does tell us something, and on Monday we'll talk about what it means. I just don't want to do too much all at once. So I'll tell you what it actually means, but that's how we find our slant asymptote. Okay. All right, so let's look at number 2. I need to factor, so I will factor out a 2x. That leaves me with x minus 2 over 2x. Am I going to have point discontinuity here? Yes. So even though it doesn't ask me for it, I'm going to write it down because you never know, you might need it later. And so I know that my x value would be at 0. So then these cancel out, and I get f of x is equal to x minus 2. So that's my reduced function, because that's what I have to use. So let me finish my point discontinuity here. This will just be -2. Then my actual answer for my slant asymptote, well, it says it occurs when the reduced rational function contains an x in the denominator. Do I have an x in the denominator? No. So the answer is none. And if I was to graph this, what would this graph? A line. We could argue the fact that it's a line, so it's its own slant asymptote, but we're not going to go there right now because I don't want your little brains to explode or anything. We're going to go with none. Okay, so then 3. So I could factor the numerator, but before I even try, the only way anything's going to cancel out is if I can factor a 2x out in the numerator. Can I do that? No. So if that factors into 2 binomials, great. It doesn't do anything for me right now, so I'm not even going to worry about it because all I'm worried about is my slant asymptote. This degree is 1 greater than this one, so I can do that. Can I use synthetic division here? No. That sucks. So we've got to use long division. So 2x, then again I make sure I don't have any missing terms, and I get 2x squared minus 4x plus 3. So 2x goes into 2x squared, x times. This gives me 2x squared. That zeroes out, and I bring down this, so I get negative 4. 2x negative 4x. 2x goes into negative 4x, negative 2 times. This is negative 4x, 0. Bring down my 3. And that's my remainder. So again, I just ignore my remainder. And my slant asymptote is y equals x minus 2. Which 1, 2, and 3 all had y equals x minus 2 in it. Total coincidence. I don't know what. Oh, I even did that. If I had tried to do that, it probably never would have worked out. Sorry, I'm going to fix my box. All right. So let's talk about number 3 again. There's another way to think through this when the denominator is a monomial. So let's think about just this as a fraction. Another way to write this is if I split the fraction up, I could make this into 2x squared over 2x minus 4x over 2x plus 3 over 2x. Do you agree that that's the same thing, like before we combine it? So then if I take this and I reduce it, this 2x cancels with one of those and the 2, so I'm left with x. This 2 cancels with the 4 and leaves me with a negative 2, and the x's cancel out. And then that's my remainder, and I get the same thing I got over there. So when it's a monomial, that's kind of a way to avoid the long division. And if you want to do it that way, I'm fine with that. I just don't want you trying to do something this way when it doesn't really work that way, and then making stuff up. So I thought I'd show it to you, but this wasn't that bad when it's a monomial anyway. All right, so let's look at number 4. I'm going to have you actually finish it off, but let's start with the factoring part of this. So I'm going to rewrite this right here. So I've got 2x cubed minus 4x squared plus 9x minus 7. If I have 4 terms, how do I attack this as far as factoring goes? Grouping. So I'm going to group this. I'm going to factor out a 2x squared. That leaves me with x minus 2. Out of this, all I can factor out is a 1. That leaves me with 9x minus 7. Do I have a problem here? Yes, because the only way I can actually finish this with grouping is if these two things match, and they don't. Okay? So since they don't match, this grouping isn't working for me, which means I can't factor the numerator. And since I can't factor the numerator, I don't even care if I can factor the denominator because nothing's going to cancel out anyway. You with me on that? So there's no holes. I can't cancel anything out, but I want you to find the slant asymptote now. Then what are you going to have to use? Long division, which looks way worse than it is in a situation like this. Uh-huh. Oh, yeah, I just didn't change my sign. Sorry, thank you. All right, what questions do we have? Anything? Don't agree with me? We're all good? Okay. So your assignment is in Delta Math, and you do not have to turn in work. And then the checklist for today, and I put this in the instructions, it says that make sure you do the assignment that's due today. I would have sworn I took that statement off, but apparently I didn't. I must have taken it off the wrong one, but there's not an assignment due today. At least I don't think there is. I've thought through that a million times. I don't know why I put that. So anyway, just want to make sure you know that.